Problem 1. In this problem, we're told that the maximum depth that any body has dived to is 313 meters. So the depth is equal to 313 meters. And we're told if seawater has a density of 1030 kilograms per meter cubed, calculate the pressure on the diver at this depth. So here's our diver down here. Above him, he's got 313 meters of water, and this surface area here is the surface area of the diver. And then this is the top of the water up here. So up here there's 1 atmosphere of pressure, which is equal to 1.01 times 10 to the 5 pascals. So to calculate the pressure on the diver, he's got this atmospheric pressure acting on him, and he's also got the pressure which results from the weight force of the 313 meters of water. So pressure is equal to force over area, which is equal to mg over area. So the mass of this water, well, we know that for fluids, the mass is equal to the density times the volume. So this is equal to the density times the volume times g over the area. And the volume of this prism is just equal to its height times the surface area. So we can put this as density, and then the volume is HAG on the surface area. And those surface areas cancel out. So we've got the rho Hg. So this is the pressure caused by the water. So the total pressure is equal to the 1 atmosphere plus the rho Hg. So let's substitute everything in. We've got 1.01 times 10 to the 5 pascals plus the density of water, which is 1030, times the height, which is 313, times g, the acceleration due to gravity on Earth, which is 9.80. So solving this on the calculator, we end up with 3.26 times 10 to the 6 pascals of pressure. And we've given that to 3 significant figures because all the data in the question was given to 3 significant figures. Okay, problem 2. In this problem, we're asked what depth does a diver need to dive to experience 2 atmospheres of pressure if the density of seawater is 1030. So the density is equal to 1030 kilograms per meter cubed, and the pressure we want is 2 atmospheres. So we do this one in a very similar way to the last question. We've got our diver, he's at some depth h that we want to find. There's 1 atmosphere of pressure acting from the atmosphere, and so we need the pressure due to the water to also be 1 atmosphere. So we've got that P total is equal to the pressure due to the atmosphere plus the pressure due to the water, and the pressure due to the water is equal to the force over the area from the water, which is the weight of the water over the area, which is equal to the density times the volume times g over the area, and the volume is just h times this surface area. So this is equal to rho HAG on A, which is just the rho Hg. So we know that 2 atmospheres, which is 2.02 times 10 to the 5, is equal to 1 atmosphere, 1.01 times 10 to the 5, plus, this is just substituting into this equation, rho Hg, which is 1030 times h times 9.8. So now we need to rearrange to find this h. So we can subtract this from this, and we've got 1.01 times 10 to the 5 is equal to 1030 times 9.8 times h. So h is equal to 1.01 times 10 to the 5 over 1030 times 9.80. And solving that on the calculator, we end up with 10.0 meters. So he needs to be exactly 10 meters under the water to experience double atmospheric pressure. Problem 3. So in this problem, we're asked about this weather balloon again. So here's our weather balloon. It has a volume of 2.3 meters cubed near the Earth's surface, and it rises up into the atmosphere. It's filled with hydrogen, and we're told that the density of hydrogen is equal to 0.0899 kilograms per meter cubed. This is the density at the surface of the Earth. And we're asked to describe what would happen to the pressure outside the balloon as it rose through the Earth's atmosphere. Okay, so here's the Earth. As the balloon rises through the Earth's atmosphere, the pressure outside decreases, and so the pressure inside the balloon must decrease as well. So as the balloon rises through the Earth's atmosphere, the pressure outside the balloon decreases as there are less air molecules colliding with the sides of the balloon. So eventually when you get into space, you're virtually in a vacuum. So most of the molecules that make up the Earth's atmosphere are close to the surface of the Earth. Okay, so as the pressure outside the balloon decreases, the volume of the balloon is going to increase because there'll be less force on the walls of the balloon holding it in, and so this will allow it to increase. So as P outside goes down, the volume is going to go up, and as the volume goes up, because of the ideal gas law, PV equals nRT, from about 10 kilometers to about the 33 kilometers, the temperature of the atmosphere is relatively constant. So if the volume goes up, then the pressure has to go down. So this is going to mean that the pressure inside the balloon decreases. And it says the weather balloon described in the question has reached a maximum altitude of 33 kilometers. What happens to the balloon at this altitude, and why can it not go higher? Okay, so at that altitude, the weather balloon is going to pop. At 33 kilometers, the weather balloon and it's going to do that simply because the volume of the balloon is increasing, and there's a limit to how much the volume can increase because the surface is made of rubber or some other material, and when that gets spread out too thinly, it's going to rupture and pop. So this is because the volume increases, making the walls of the balloon very thin. There is a limit to how thin they can be without popping. So if you wanted to go higher than that, you're going to need to make stronger walls on your balloon. So it pops basically for the same reason that if you blow up a party balloon, it pops when it gets above a certain volume. Problem 4. So in this problem, we're told that water flows through the pipes shown below from left to right. So it enters here and it's coming out here. And we're asked to A, rank the volume flow rate at the points A, B, C, and D. So A, volume flow rate. So this is the volume per second passing through the pipe, which we can use the formula AV is equal to constant. So this is the volume flow rate, and this tells us that it's constant throughout the pipe. So volume flow rate is the same at A, B, C, and D. Okay, part B says rank the velocity of the fluid at the 4 points A, B, C, and D, and we need to give an explanation. So to rank the velocity, we will use this volume flow rate equation. We know that the area at A times the velocity at A is equal to the area at B times the velocity at B, which is equal to the area at C times the velocity at C, which is equal to the area at D times the velocity at D. And we can see that D has the biggest cross-sectional area. So cross-sectional areas are just the surface area of the pipe if we were looking from the end. The surface area at C and D is the same, and A is the smallest. So we know that the area at A is less than the area at B, which is equal to the area at C, which is less than the area at D. So if this one is largest, then the velocity at D needs to be smallest in order for all of these things to be equal. So because A has the smallest cross-sectional area, it has the largest velocity. So the velocity at A is greater than the velocity at B, and B and C are equal because they've got the same cross-sectional area, and D has the smallest velocity as it's got the largest cross-sectional area. So part C, we need to rank the pressure at the 4 points. So to rank the pressure, we're going to need to make use of Bernoulli's equation. We've got that the pressure plus rho GH times the height plus a half rho V squared is constant. Now let's just compare points next to each other. A and B, they're at the same height. So this, we know that the pressure at A plus a half rho VA squared is equal to the pressure at B plus a half rho VB squared. The height's the same, so this term would cancel out on either side. And now the velocity at B is smaller than the velocity at A. And so this tells us that the pressure at A must be smaller than the pressure at B to make up for that difference. So the pressure at A is less than the pressure at B because this term for A is larger. Okay, let's now compare B and C. They've got the same velocity, but their heights are different. So we'll do this over here. We know that the pressure at B plus rho G times the height at B is equal to the pressure at C plus rho G times the height at C. Now, C has a smaller height, this is lower, and so this must be higher to make up for that difference. So we know that the pressure at C is greater than the pressure at B. And since the pressure at A was less than the pressure at B, and B is less than C, we can add that to the expression. So let's now compare C and D. C and D are at the same height, so this term doesn't play a role. It's just the velocity terms that will. So we know that the pressure at C plus a half rho VC squared is equal to the pressure at D plus a half rho VD squared. And the velocity at D is smaller, so this is smaller, and so the pressure at D has to be larger to compensate for that difference. So the pressure at D is greater than the pressure at C. So we can add this to this expression over here as well, and so we've got the pressure at D is the greatest pressure. So D has the largest pressure, followed by C, B, and A. Problem 5. So we're told that the water tank shown here is open to the atmosphere. So we've got 1 atmosphere of pressure acting up here. And we need to find an expression for the speed of the water leaving the tank here. So this question is actually fairly challenging. To answer it, we're going to need to use Bernoulli's equation, that the pressure plus rho GH plus a half rho V squared is constant. And so one of the places we'll be considering is right here, where the water's leaving the tank. We'll also want to consider the water just inside the tank, just on this side. So let's call this one location 1 and this one location 2. So what we'll do is we'll write down everything we know about these locations. So we know the pressure at 1, it's caused by the atmospheric pressure acting on the top of the tank, so that's equal to the pressure of the atmosphere, plus it's also caused by the weight force of the water there, so that is plus rho GH. We showed this equation for the pressure in problem 1 and 2 if you want to see how we derive that. So the pressure at 2, once it's left the tank, it's just open to the atmosphere, and so this is equal to the atmospheric pressure. Now rho GH, this is telling us the height of the point above ground level. These are at the same height. So we know that rho GH1 is equal to rho GH2, just because water's got the same density, and H1 and H2, the height of these points above ground level, is the same. So that part will cancel out. And so now we've got to work out the velocity. So we know that the velocity at point 2 is equal to the velocity that we're trying to find, the velocity that we need an expression for. So this leads us to the tricky part. We need to work out the velocity at 1. Now, to work out the velocity at 1, we're actually just going to approximate it. The velocity at 1 is very small. Okay, so how do we know that V1 is very small? Well, it's because we know that the flow rate is constant. So A1 V1 is equal to A2 V2. Now the cross-sectional area here is very small. So this is small, as the opening on the tap's small, and that gives us the cross-sectional area here. Whereas this cross-sectional area here is the entire tank. So this is large. So we know that if this is large, then V1 has to be a lot less than V2. So we can approximate V1 as 0. So now what we need to do is substitute everything into this equation. We're going to ignore this term here because 1 and 2 are at the same height above ground level. So we've got P1 plus a half rho V1 squared is equal to P2 plus a half rho V2 squared. And now we'll substitute everything in. P1 is the atmospheric pressure plus rho GH. V1 is approximately 0, so that term's actually 0, so we can leave it off. P2 is atmospheric pressure plus a half rho V squared, where V is the velocity we're trying to find. So these atmospheric pressures cancel out, and we have rho GH is equal to a half rho V squared. So these rho's cancel each other out. And so we've got that the V squared is equal to 2GH, and so the velocity is equal to the square root of 2GH. And that is how we can solve that problem. So this is problem 6. We're shown an image of water leaving a tap, and we're told that the measuring cylinder collects 475 millilitres of water in 1 minute. And we're told that at the top, the water has a diameter of 0.700 centimetres. Now in part A, we're asked what is the volume flow rate for the water leaving the tap. So we know that volume flow rate is equal to the cross-sectional area times the velocity, and it's also equal to the volume over the time. So these are two different V's. This is the velocity and this is the volume. So we know the volume and the time. So in 1 minute, 0.475 litres leaves the tap, and that's in 60 seconds. So we can calculate this. We get 7.917 times 10 to the minus 3 litres per second, except let's put it into SI units, which is meters cubed per second. 1 metre cubed holds 1,000 litres. So to convert this from litres per second into meters cubed per second, we're going to have to divide it by 1,000. So that will give us 7.92, just putting it down to 3 significant figures. Now dividing by 1,000 gives us 10 to the minus 6 meters cubed per second. So that's the volume of water leaving the tap each second. Now part B of the question says, what is the velocity of water leaving the tap? So in this case, we're going to need to make use of this part of our volume flow equation. So we know that the cross-sectional area times the velocity is equal to 7.92 times 10 to the minus 6 meters cubed per second, and we'll need to work out what the cross-sectional area is. Now, the water leaving the tap is shaped like a circle. We know that its diameter is equal to 0.700 centimeters, and so the radius is half the diameter, is 0.350 centimeters. So what we can do is substitute this into the area of a triangle formula. So the area is equal to pi r squared, so that's equal to pi times 0.350 squared, and solving that on the calculator, we get 0.3848 centimeters squared. But now it's always good to convert everything to SI units so that we don't end up confusing ourselves. In 1 meter squared, we've got 100 centimeters along here and 100 centimeters along there, so there's 100 times 100 centimeters squared. So we need to divide this by 100 times 100, which is 0.3848 times 10 to the minus 4 meters squared. So now we've got our area, and we can rearrange this to get our velocity. So the velocity is equal to 7.92 times 10 to the minus 6 meters cubed per second over the area, which is 0.3848 times 10 to the minus 4 meters squared. So these meters squared cancel with those meters cubed, and so our final units is meters per second, which is what we wanted. So this gives us a velocity of 0.206 meters per second. So that's the answer to part B. Part C, we're asked, what is the velocity of the stream 20 centimeters below the tap? So to do this, let's call position 1 the top of the tap and position 2 20 centimeters below. Okay, so what we're going to need to use is Bernoulli's equation. So we know that pressure plus the density times gravity times the height at position 1 plus a half the density times the velocity at 1 squared is equal to the pressure at 2 plus the density times the height at 2 plus the velocity at 2 squared. And now this is all open to the atmosphere. So the pressure at 1 and the pressure at 2 are both just atmospheric pressure. So these cancel each other out because the same term appears on both sides of the equation. Now rho is a common term to each of the remaining terms. So rho actually cancels out as well. And what we're trying to find out is the velocity at the bottom. So this is the term that we want to find. So let's simplify it a bit by multiplying all the terms by 2. That will get rid of these halves. So we've got 2gh1 plus V1 squared is equal to 2GH2 plus V2 squared. So let's rearrange it and make V2 squared the subject. So we've got V2 squared is equal to 2G, and now on this term side we've got H1 minus H2. That 2G is a common factor, and then we've got plus V1 squared. So now we know what all of these things are. We don't know H1 and H2, but we know that H1 is 20 centimeters above H2. So we know that H1 minus H2 is equal to 20 centimeters, which is 0.20 meters. So let's substitute in. We've got 2 times 9.80 times 0.200 plus the velocity at 0.1 squared, which is 0.206 squared. So solving this, we end up with 3.9624. And so the velocity at 0.2 is equal to the square root of this, which is equal to 1.99 meters per second. Okay, now part D asks us what is the diameter of the stream 20 centimeters below the top. So hopefully we've got enough room here to do it. What we're going to need to do is use that the volume flow rate is constant. So we know the velocity of the stream, and we can use that to get its cross-sectional area. So let's start by doing that. So D, we've got that A to V2 is equal to the same as it was up the top, so that's 7.92 times 10 to the minus 6, and we know this velocity, so that tells us that the cross-sectional area at 2 is 7.92 times 10 to the minus 6 divided by 1.99, and so this is equal to 3.97 times 10 to the minus 6 meters squared. Okay, now we're going to need to make some more room. So we've got that the cross-sectional area is equal to 3.97 times 10 to the minus 6 meters squared, and that's the cross-sectional area of a circle, and what we need to know is its diameter. We can work out its radius. We know that this is equal to pi r2 squared. This is the radius at point 2. And so that tells us that r2 squared is equal to this divided by pi, which is equal to 1.266 times 10 to the minus 6 meters squared. And so the radius is the square root of this, is 1.125 times 10 to the minus 3 meters. And so the diameter at point 2 is 2 times the radius, and so that is equal to 2.25 times 10 to the minus 3 meters. So that's our answer in meters, so that is 2.25 millimeters, or we could put it if we wanted in centimeters, which is 0.225 centimeters. And so that's the final answer. So this is problem 7. This problem says crude oil has a viscosity of 0.07515 Pascal seconds. So let's make a note of that. Viscosity is equal to 0.07515 Pascal seconds. And the density, so rho, is equal to 858.5 kilograms per meter cubed. An oil rig is designed to pump 3 meters cubed of oil each minute. So volume over time is equal to 3.00 meters cubed per minute. What is the minimum diameter the pipes could be designed with in order to avoid turbulent flow? So we want to know what's the diameter of the pipes. So to completely avoid turbulent flow, we're going to want to be in that laminar flow region. So we're going to want our Reynolds number, which is equal to rho v d on the viscosity. Rho is the density, v is the velocity, d is the diameter of the pipe, and eta here is the viscosity. We need that less than 2,300 to ensure that we have laminar flow. So we're going to need to substitute in here. We've been given the density and we've been given the viscosity. We're going to need to work out the velocity here. So we can do that using our volume flow equation. We know that the volume over the time is equal to the cross-sectional area of the pipe times the velocity of the pipe. This gives us the volume of liquid flowing through the pipe per second. And so the cross-sectional area, this is a circle, so it's got an area which is equal to pi r squared, and then we'll keep the velocity, but we want everything in terms of the diameter, so the radius is half the diameter, so we can put this as pi d on 2 squared v, which is equal to pi d squared v, that's a v, on 4. So we've now got our volume over time, and we're told that this is 3.00 meters cubed per minute. So we should put this into seconds so that this velocity is then in meters per second as well. So in 1 minute there's 60 seconds. So we divide that by 60 like that. And so this tells us, rearranging it to get the velocity here as the subject, the velocity is equal to, this whole side is 0.05, so this is 0.0500 times the 4 divided by the pi d squared. So this gives us a velocity of 0.06366 over d squared. So we've now got the density and the viscosity and the velocity. So let's substitute this in. So we've got the density, 858.5, times the velocity, which is the 0.06366 over d squared, times d, over the viscosity, which is the 0.07515, has to be less than 2,300. Now this d squared will cancel with this d, so we'll end up with just 1d on the bottom. So we can work out the numbers on this side. This gives us 727.26 over d, and that has got to be less than 2,300. So that gives us d has got to be greater than 0.3162, and that's in meters. So we should give it to 3 significant figures, as this one here's to 3 significant figures. So this is equal to 31.6 centimeters for the diameter for our pipe. And then the question goes on, why is turbulent flow undesirable? Well, we want to minimize turbulent flow because it requires more energy to push the oil through the pipes when we have turbulent flow. So turbulent flow should be minimized to minimize the energy needed to push the oil through the pipes. Problem 8. So problem 8 says a blood vessel has a blockage in it that decreases its cross-sectional area to 1/4 its initial size. So here's the initial size of the blood vessel, and it's got some blockage. So this is A healthy, and here this has got some cross-sectional area A blocked. And this is equal to 1/4 the healthy one. We're asked to write an expression to describe the speed of blood through the blocked vessel, V blocked, compared to the speed of blood through the healthy vessel, V healthy. Okay, so we know that AV is constant. So A healthy, V healthy is equal to A blocked, V blocked. And we know that A blocked is a quarter A healthy. So this is a quarter A healthy, V blocked, A healthy, V healthy. So you can see this A healthy occurs on both sides, so it's a common factor and cancels out. And so V blocked, just rearranging this, is equal to 4 times V healthy. So the blood has to flow 4 times as quickly through this blocked part. The question goes on, making the assumption that the same volume of blood needs to pass through the blood vessel when it's healthy as when it's blocked, and then we're asked, is this a valid assumption, and discuss. Well, I mean, it's fairly valid because this blood is needed by the body to provide oxygen. So your body doesn't suddenly need less oxygen because some of your arteries are a bit clogged. So yes, that is a reasonable assumption. It's possible it doesn't happen as much, so when you start to get clogged arteries, you do in fact get a bit less blood flow, and so your body in general becomes less healthy because you've got less oxygen going to all the parts of your body and less chance for those parts of your body to lose their carbon dioxide as well. But it's a fairly reasonable assumption. Problem 9. So some dinosaurs had neck lengths of up to 15 meters. So here's dinosaur's heart, here's its neck. There he is, and this distance we're assuming is 15 meters, and this is the height of its head, and this is the height of its heart. If a dinosaur's brain was 15 meters above its heart and the brain required a blood pressure of, okay, so here it is, the blood pressure is equal to, let's do it in pascals, 10,640 pascals. So this is the pressure in the head. We're asked what pressure would the dinosaur have at its heart? And we can assume that the density of dinosaur blood is 1,050 kilograms per meter cubed, similar to humans. And we can also assume that the blood vessels have the same size up here as down here. And if they have the same size, because AV is constant, that tells us that V is constant. So what we can use is Bernoulli's equation. We know that the pressure in the head plus a half rho V head squared plus rho G H, the height of the head, is equal to the pressure at the heart plus a half rho V heart squared plus rho G, the height of the heart. Okay, now we've just said that the velocities are the same, so this term and this term are the same, so they will cancel out. And what we're trying to work out is the pressure in the heart. So the pressure in the heart is equal to the pressure in the head plus rho G H head minus rho G H heart. Now what we can see from this diagram is that the height of the head is equal to the height of the heart plus 15, or the height of the head minus the height of the heart is equal to 15, just rearranging this equation. So we've got that the pressure in the heart is equal to the pressure in the head, which is 10,640, plus rho GH, rho is 1,050, G is 9.8, and then we've got the height of the head minus the height of the heart. So combining these two terms, taking the rho G out as a common factor, and then using h head minus h heart is 15, we can put 15 in there. And so this lets us calculate the blood pressure, which is 164,990 pascals. So if we want to get from pascals to millimeters of mercury, that's 1,240 millimeters of mercury. Now this is an enormous blood pressure. It's unlikely that the dinosaur's heart could have coped with this much pressure. So the question asks us if we can think of any modifications or behaviors that may allow them to cope with this pressure. So it's actually highly unlikely that the dinosaurs held their necks vertically. They probably walked with their necks relatively horizontal so that they didn't have this massive pressure change. They would have also had to have all those one-way valves like the giraffes had in their blood vessels to stop the blood flowing in the wrong direction if they put their head down to have a drink. And problem 10. So in this problem, we're told that the total change in height of water passing through the Snowy Mountain scheme is 800 meters. This water is used to produce 4,480 megawatts, so that's times 10 to the 6 watts of power. Assuming that 1/4 of the gravitational potential energy of the river is converted into electrical energy, so the efficiency is equal to 25% or 0.25, that's 1/4. We're asked what is the volume flow rate of water through the Snowy Mountain scheme. So we know that power is equal to energy over time. In this case, we're using energy in the form of gravitational potential energy stored in the water. So this energy is mgh over the time, and then we need to times it by the efficiency. Okay, so we've got the power, that's 4,480 times 10 to the 6 is equal to m on t. Those are things we don't know, but if we can work out the mass that passes for each unit time, we can work out the volume flow rate. So times 9.80, that's g, times the height, which is 800 meters, times the efficiency, which is 0.25. So rearranging this, we can find that m on t is equal to 4,480 times 10 to the 6 divided by 9.80 times 800 times 0.25, just dividing by these. And so we end up with 2.286 times 10 to the 6 kilograms per second. Now we need to get the volume flow rate. This is the mass per second, but we know that if we have a meter cubed of water, it contains 1,000 liters, so 1,000 kilograms. And so to convert this from kilograms to meters cubed, we need to divide by 1,000. So this is equal to 2.286 times 10 to the 3 meters cubed per second. Now we've probably got too many significant figures there. We've got 2 or 3 given in the question, so let's give this to 3. This is 2.29 times 10 to the 3 meters cubed per second is the volume flow rate.